Bismillah ar-Rahman ar-Rahim. Welcome back our student to Electrical Circuit 1, new topic, series circuit. In this topic we will try to cover different subtopics like series resistors, series circuits, power distribution in a series circuit, voltage sources in series, Kirchhoff's voltage law, and finally voltage division in series circuit. As you know, we are dealing with the textbook, which is Introductory Circuit Analysis. The edition is 13th, and this is by Robert Boylested. Today we will try to understand what does it mean by series. And in these examples we have two figures. 5.4 contains the three elements, and 5.5 also contains the three elements. What is the main difference between those two elements? Actually, the answer is the configuration, the arrangement of the resistors. Now, in figure 5.4, we can notice that R1, R2, R3, they come after each other by one side. So R1 with R2 connected here from one side. Just 1 minute here. Okay, from one side, which is this side, from R1 and R2 one side, and again R2 with R3 again one side. This side here, we call it point. So R1 with R2 connected by how many points? Only one side or point. R2 with R3 connected by how many sides? Only by one side, which is called point. So once any two resistors are joined between each other by one side or by one point, we call those resistors in series. However, in this example 5.5, we can see here those two resistors here, R1 with R2, yes, they are joined by one point, but this point, unfortunately, carrying another element, which is R4. So in this configuration, we cannot call it series. Why? Because it's supposed to be between R1 and R2 only one point, and this point is not carrying any other element or joint another element. Suppose if we eliminate this one, so I only have this one, R1 and R2, yes, I can call it series resistors. But at the same time here, since I have here three loads joined by one point, this one, so this configuration actually called star configuration. Anyway, it doesn't matter about now what is the name of the other configuration, or what our concern is whether these resistors are in series configuration or not. So the series configuration only connected by one point, only by one point. Now, how to add these together? In simple way, just algebraic sum, add them as R1, R2, R3 plus R4 plus Rn equal to the total resistance of those resistor or the configuration. For examples here, just to emphasize the main concept, that if we have here four resistors, R1 with R2, of course, this is as one point here, joined together, means resistor. R2 with R3 again, as one side or one point. And finally, R3 with R4, again, one side by one point. So all the three resistors here are connected in series. Then I can add them together by algebraic sum, R1 plus R2 plus R3 plus R4, substitute their values 20, 22, 20, 1.2K, 5.6K, then you can find the total resistance of 7.04 k ohm. Similarly here, only the difference that the value here for each resistant same as the other value for the other resistors. So the value here 3.3, here 3.3, here 3.3, here 3.3. So how to add them together? Just the total resistance will be the number of the resistor plus the value of this resistor. So 4 times only get one resistor, which is 3.3. So 4 times 3.3 gives 13.2 kilo ohm. Series circuits. The series circuit actually you will deal with the same principle of how to call the circuit is series or not. As we mentioned previously about the series, it's supposed to be those resistors joined between each other by 1 point. For example here, R1 with R2 connected with this point, which is B, and this point here, A connected to the supply and C connected with the same supply. So what I get here, actually I get loop. This is called closed loop or closed path. So the circuit basically is closed loop or closed path, means the flow of the charge or the current as conventional current here is start from the source, then go through R1, then go through R2, then back again to the same point, which is the source. We call this one a closed loop. So a closed loop means you start from point and back again, passing through different loads and back again to the same point. We call it circuit or closed loop. But we have another condition for the series circuit, which is the flow of the current here is supposed to be is not branching or carrying another element, like this figure here 5.4. I have here R1, R2, and at the same point, which is B, connected with another resistor here R3. So in this case, I can't say this configuration is series. Why? Because this point here is carrying another element. So it must be no element with the same point. So the flow of the current goes from the R1 and to the R2, then back again to the source if I have source, okay, then back again. So this closed loop, we call this one series circuit. How to add those resistors if you have a voltage supply? Just imagine this I here as a voltage source, like this one. So between those terminal A and B, you look through all resistors here. So you will shrink R1 with R2 with R3 here as one resistor, combining all together as one resistor, which is 140 here. Then you will find this circuit here. This is the 140 here, and this is your source. Then you can apply Ohm's law, which is E over R total. The point here, always remember that when you want to simplify the circuit, you can only look at the source side, then go through inside the circuit, and you can start reducing the load. It's become clearly when we deal with series circuit, it's become more clearly when we deal with complicated circuit. When we go through simplification, then we can find the currents, the voltage drop, and so on. Just remember now this note from where you will apply the simplification opposite of the source. What are the properties of the DC series circuits? It's important to know the series circuits has some properties, and these properties helps you to make your calculation faster and easier. For example, one of the property of the DC circuit is the flow of the current same, which is mean the flow of here from the source as I supply here, go through I1, R1 here, go through R2, go through R3, go and back again as a closed loop to the same source without any distributing to any other way. If I have, for example, this, so the current goes through here and the other go from there. So in this case, this is not a series. But since this circuit is a series here, so I have this property, which is the current through all resistor maintain the same current of the source. So the I supply equal to I1 equal to I2 equal to I3. As we agreed, also the direction of the current is conventional direction. What does it mean, conventional direction? Mean the flow of the current start from positive, then back to negative. This is mean conventional direction. The second property of the series circuit, which is the voltage drop. The voltage drop depends on the value of the resistor here. More value or large value, okay, has high voltage drop. So the 100 here has highest voltage drop than the other resistor here. So we apply the voltage or Kirchhoff voltage law, which is E equal to V1 plus V2 plus V3. So the summation of the voltage drop here, it gives the supply. The polarity of the voltage across a resistor is determined by the direction of the current. So always where the direction of the current, if the direction of the current from this side, you will put the polarity is positive. The current leave the resistor here with negative. Again, in the opposite side here, once the current passing from this side, then gives positive, leaving negative. Any side here, for example, this side you go from the low, which is positive, then leave negative. Anyhow, the direction of the current indicate to the polarity. The voltage drop, as you know, by the Ohm's law, for V1 I1 R1, for V2 I2 R2, for V3 I3 R3. Just remember that the higher resistor value, higher voltage drop. Example here. Within this configuration, a series circuit, we need to find the total resistance. How much the total resistance? Simply add them together. R1 plus R2 plus R3 gives 8 ohm. Then I need to find the supply current. By using the Ohm's law, the supply current equal to the supply voltage over the total resistance, 8. This is for the total resistance, and the supply voltage is 20 volt. It gives the supply current, which is 2.5. So 2.5 of the supply current starting from here as conventional direction to here, then gives positive because the current passing from this side, leaving negative, then passing through here again, the 2.5 ampere, through here, through here, through here, through here, through here. Mean the 2.5 ampere here will be the same in the whole closed path. So the 2.5 goes from the positive and back again to the negative. The only you have to consider the voltage drop across each load. So how much the voltage drop here? You multiply 2.5 times 2, which is 5 volt. The 2.5 times 1 gives 2.5. The 2.5 times 5, which is 12.5. Add them together, you will find the supply. Just try the E equal to V1 plus V2 plus V3. It gives the value of the total supply. So this, as we know, is the Kirchhoff voltage law. Now, in this example here, I have the total resistance is given. I have also the current I3. Then I need the unknown, the supply and R. For this question, you be careful because some unknowns is already, you can find it within the properties of the circuit. For example, if I want the current passing through the R2, actually it's the same of I3, which is 6 milliamp. This is a series circuit. And I know the property of the series circuit, the current will be the same. So the current starts from positive through the all resistors here and back again as 6 milliamp. So you have here the current, you have here the resistor, then I can find the voltage drop here. What is the V3? V3 equal to I3 by Ohm's law times R3. What is the V2 here? Similar here, multiply the 6 milliamp times 4K, will find V2. What is the R1? You can find first the supply. The supply is, you have here the total resistance, you have here the total current or supply current. So E equal to I times RT. You have here the 6 milliamp, which is 10 to the power minus 3, times the total resistance here, 12 times 10 to the power 3. Here is K and here is M. I can cancel this one with this one, 10 to the power minus 3 with 10 to the power 3, then I multiply 6 times 12, which is 72. Well, I have here the voltage supply here, I have V3, I have V2, okay, then I can find the V1. Since I have V1, I have I1, I can find R1. The solution here, it comes easily for different way. You can find also at the beginning the R1 just by subtracting R2 plus R3 minus R total, it gives R1. What I want to say, you have actually different ways to solve the problem. It's not necessary to follow my way because you have different way and lead the same answer. You can start from any point. you can go through the clue of this one of the current here. You can go from the clue of the total resistance here. Anyway, you can start from any view you like to start. Not actually restricted to follow my way. Power distribution and series circuit. In the power distribution mean there is power delivered, which is from the source, and power consumed, which is by the load. Suppose I have here three bulbs, this bulb here, this bulb here, and this bulb here. The total power, let's assume, is 15 watt. So if those resistors same value, I have here the same amount of power. Let's assume here I will absorb here 5 watt, 5 watt, 5 watt. So 5 plus 5 plus 5 equal to the delivered. So the power delivered, this is by the source, this is the delivered by the source, and power consumed by the loads. And power delivered, it must be equal to the total power consumed by each load. So PE equal PR1 plus PR2 plus PR3. Here in my note, the power applied by the DC supply must be equal the dissipated by the resistive elements. As you know, gentlemen, the formulas, we have 3 formulas. You can apply any one of these, whether for the power supply or for the resistor. But for the source, you have only apply this one, because in the source you will have only EI. You will not apply R. Whether the source have internal resistance, but we are not considering as a load. So this is for the source, and this is for the load. So P source equal to E source times I source, and for the resistors, that for example for P1, P equal V1 I1 I square 1 R1. Similarly, if you have for P2 or P3, will apply the same formula. I have here example. A series circuit consists of 3 elements, 1K, 3K, 2K. I need to find the total resistance. What is the total resistance? 1 plus 3 plus 2, which is 6 kilo ohm here. Then you need to find the current passing through all by using the Ohm's law. The I supply equal to E, which is 36 over 6 times 10 to power 3, because it's mean K. So the answer will be 36 over 6, it gives 6 times 10 to power 3 goes up 10 to power minus 3, mean you will have here 6 milliamp, which is the current here for the I supply. As we know, the current here as 6 milliamp will be the same as I1, the same as I2, the same as I3, the same as I supply, and back again. How to find the voltage drop? Just multiply the current here times the resistance by using the Ohm's law. V equal to IR. Then you can find the voltage drop of the load. Later on, you can find also the power by any form. For example, you can say the I square times R. You have the I square, which is 6 milliamp square times R. For example, 1, you will have 6 milliwatt square times 1. Similarly here, you can apply this one, or you can apply V square over R, or you can apply the I1 times V1. We have here the answer of this example here. So here is the 6 kilo ohm, this is 6 milliamp, and this is the voltage drop for 6, 18, 12. When we add them together here, it must be get 36, the source. For the power dissipated by each load, for B1, the P1 here 36, the P2 here 108, the P3 here 72. Add them together here, it's supposed to be, you get the total power. How much the total power? From the source. So the total power here, or the source power, is supposed to be the E source times the I source. What is the E source? 36. What is the I source? Which is the 6 milliamp. Multiply this one by this one, you will get 216 milliwatt. So actually you have two sides, left hand side and right hand side. So this is the how to check for left hand side and right hand side. The left hand side, which is the P supply, and the right hand side, which is the dissipated power by each load. When you add them together, it's supposed to be you get the same power delivered by the source. Another example here. In this example, actually you need the same requirement. So you have here the voltage supply. You have here the total resistance, R1, R2, R3, 2 plus 1 is 3, plus 5, which is 8. Then you will apply the same principle, the same concept of this one, and you will find the total current here. Then you will find the voltage drop across each load, the power supply, the power dissipated by the load, and you need to compare or check whether the power supply is equal to the power dissipated by the loads or not. It's supposed to be equal, and this is 50 watt here and 50 watt here, and the same procedure like previous example. Voltage sources in series. The question is, can we add the sources together in series? If I assume I have here 3 batteries, and you know the batteries, like car batteries. Okay, so yes, I can. The question, how can we add them together? It's written here by summing the sources with the same polarity and subtracting the total of the sources with the opposite polarity. Okay, what you need actually, you need to look at each source. Here is positive and negative. Put the direction of the flow, which is up from positive here, it goes from positive. The second one again positive, the flow of the current, I mean positive, from positive conventional direction. And the other one, which is last one, which is again. So all actually goes through the same direction. In this case, you add them together, 2 plus 6 plus 10, it gives 18 at which direction? Which is up direction. In example B, same. I have here the E1 from, this is the positive here, goes down, E2 goes down, while E3 goes up, because the polarity is opposing to the other polarities. So I will add the same direction or polarity, 9 plus 3, 12, and I will subtract it from 4, which is 8. At which direction? It's supposed to be go to larger direction, which is this direction, which is here. So simply, we can add the voltage sources in series only just following the direction of the current. If they have the same directions, we will add them together. If they have different directions, we will subtract. Then we can find the single source or the net of the source. You can see here, the gentleman, the way how I solved that examples here in details. I leave it for your reading. Other example here, just to emphasize the same concept, I have here 10 volt in this direction, I have 6 volt in this direction, I have 2 volt in this direction. All they go through one direction, which is to the right direction. Then I can find the single source by add them together, which is 18 volt with the same direction. For this one here, this voltage 4 goes here and the other goes to opposite. So 9 plus 3, 12 minus 4, which is 8. Okay, so in this direction. How about the real example in our life for the adding the sources, the DC sources, the remote control for the TV or for the let's say projector or toys for kids. That's it. Okay, so it's supposed to be by this way. So positive, this is the negative, this is positive, this is negative, this is positive, this is negative, this is positive, this is negative, this is positive. Okay, so 1, 2, 3, 4. We have 3 batteries here. So this is positive, here is positive, and here is positive. So if this one is 1.5, and this one 1.5, and this one 1.5, 1.5, add them together to form 6 volt. If you change any direction of this battery, actually you are subtracting from 6.5 and the remote will not work. So be careful to put the same configuration here. Negative, positive, negative, positive, negative, positive, negative, positive means you are going to one direction for all these sources. Kirchhoff voltage law. Kirchhoff voltage law. Let me go to the board. I will transfer to the board. Yeah, here. I will explain the Kirchhoff voltage law, then we can back again to our note. This is the source here, and we know that this source has two terminals, positive terminal and negative terminal here. This is the R1, this is the R2, this is the R3, say this is the R4, and so on. So the R1 here, this is the R2, this is the R3, and this is the R4. We must know that the direction of the current is from positive to negative as conventional direction, right? So the polarity based, again, as we mentioned it previously from the other slides, based on the direction of the current. So the direction of the current from this side, so it will start from positive, then negative, then positive, then negative, positive, negative, positive, negative. So this is the polarity across each load. So this is the V1, this is the V2, this is the V3, and this is the V4. What is the Kirchhoff voltage law? Kirchhoff voltage law says that the sigma here, or the total voltage here, it must be equal to all or the summation of the voltage drop. How to apply the voltage or the Kirchhoff voltage law in the loop. Of course, loop, closed loop. You must have a closed loop to apply Kirchhoff voltage law because actually you are tracing the current. You need first to make assumption. The assumption is always follow the clockwise. Of course, you can go to counterclockwise, but when I say clockwise, that is mean you can follow the standard of the book, and you will not get any mistake. So the clockwise direction. So this is your assumption. Then trace the current. Let's start from this point here, which is the source. Okay, I will start from one point and I will back to the same point. So the current here, the I here, as clockwise direction. This is number one. So number one here, number one, clockwise direction. The number two, you need to pick up the last polarity of the load. Okay, so starting from here, the source. What is the last polarity of the source? Positive. So you will write here positive source. Then the current goes here, enter here, then leave this load by this negative. So minus V1. Then the current continue here, enter positive and leaving again negative. So minus V2. Then continue again, pass it through here, positive and leaving with negative. So minus V3. Similarly here, entering the positive and leaving this negative. So minus V4. Then continue here, back to the same point, which is the source, equal to 0. Take this voltage to the other side here. So the E equal to V1 plus V2 plus V3 plus V4. Actually, this is Kirchhoff voltage law in simple way. Okay, let's back again to our slides. Our slides here. Kirchhoff voltage law. Okay, so this is the scientist, okay, Kirchhoff, who is figure out and develop this theory. And here we go. The voltage rise equal to the voltage drop. So the Kirchhoff voltage law, the applied voltage of a series DC circuit will equal to the sum of voltage drops, which is V1 plus V2 plus V3 plus V4 of the circuit. So the sum, which is here, the voltage rise, which is here, the supply. So here equal to V1 plus V2 plus. So this is the Kirchhoff voltage law. Now, let's apply Kirchhoff voltage law in this example here. Let's go through the same concept I just mentioned it to you. Okay, we will assume the direction is clockwise direction. We already have here the polarity is given from the question here, the example, just writing down the equation. Okay, I will start from the supply. So E with positive, then the current here passing through here. So I will leave the V1 with negative, so minus V1, then enter here. I will leave the minus 4.2 volt, then I will go through here, then to this supply by this negative minus 9 equal to 0 when I back to the same point. So this equation basically the same equation here. Then you can substitute, you will find the unknown, which is the voltage drop across this resistor. Another example here, apply or use Kirchhoff voltage law to determine the unknown. What is the unknown here? Here the unknown. The same here. I will go for the clockwise direction. Then let me start from the source, which is a plus 60, then minus 40, minus Vx, then plus 30, back again to the same point, equal to 0, which is your equation here. Then you can find this unknown by add them together, then take this one to the other side, you will find the answer for the unknown one. Another example here, you can start from anywhere to find the Vx. What is the Vx? Here is the Vx. So if I start from this way as clockwise, then you will say the last polarity here is minus 6, then minus 14, then minus, because when you apply the conventional direction here, so you will follow the flow of the direction, so minus Vx, then a plus, the last polarity here, a plus 2 equal to 0, which is your other example here. I have Vx here, or the x here. I have two, let's say, two paths. Okay, let's start the first path from here. Anyway, it's given the direction here. So the direction already is given here as clockwise direction. So only what you need, start from one point. For example, you will start from the supply. So positive E minus 12, then minus Vx equal to 0. This is for path 1. So you substitute here the value, which is 32 minus 12 equal to Vx. You can find Vx here. Similarly here, you can start from any point, from, for example, here, then back to here, which is minus 6, minus 14, then a plus Vx, because this is the positive, negative, minus Vx, sorry, minus Vx. This is the Vx here with minus here, okay, equal to 0. Okay, so add them together, you will find again the same. So basically, you are dealing with the same principle. One, make your assumption clockwise direction. Two, pick up the last polarity of the element. I have here another example for the Kirchhoff voltage law. I will take the direction is given there. Okay, so you can also put your direction here. So here minus E, a plus V3, a plus V2, a plus V1. Take this one to the other side. So V1, a plus V2, a plus V3 equal to E. This is the same equation, you have it here. Then you can find the I1, I2, and the other unknowns by using the Ohm's law. So this is the idea here of the Kirchhoff voltage law. So now we have two ways to find the voltage. One, by using the Ohm's law. I can find the voltage, which is by I, R. The second one by using Kirchhoff voltage law. I have now third method to find the voltage called voltage divider rule. What is the voltage divider rule here? This is another method to find the voltage across the resistor by applying this formula. For example, you need to find the voltage drop here. Only what you need, multiply this resistor for R1 times the supply over the total resistance. You can find V1. If you want to find V2, again, V2, the supply times R2 over RT. Very simple formula and really good formula to find the voltage drop without using Kirchhoff voltage law and also without using Ohm's law. We have here example to apply the voltage divider rule. So I have the total supply of 45, 2K ohm, 5K ohm, 8K ohm. What is the V1? As we mentioned, V1 equal to the source times R1 over total resistance. The source is 45. The R1 is 2 kilo ohm. The total resistance 5 plus 2 plus 5, 7. 7 plus 8, which is 15. So you will get 6 volt. The other one, the same formula, you will get 24. When you add 6 plus 24 plus the, what is the V? You can find also here V2. What is the V2? Which is E45 times 5K over 15. The value here, a plus the 24, a plus 6 volt, it must be gives the total supply. So the voltage divider rule is a simple formula, can be used to find the voltage drop across any load just by multiplying the source times the Rx over the total resistance. Example here, I have the source 24. This is the positive and this is the ground negative. We can connect it together here as redraw here. So 4 ohm, 12 ohm, 24 volt. We apply voltage divider rule. R times E over R1 plus R2. So R times 24 over 6, it gives 16. Similarly here, for the R2 times E over R total gives 8. So 6 plus 8, 16 plus 8 equal to the source. As simple as this. Well, here, what else? Yeah. Actually, this is the homework. You attempt this homework. Very simple homework. This is a series configuration here. You need to find the voltage drop, you find total resistance, okay, and so on. Similarly here, you need to apply for the Kirchhoff voltage law, and This here, the unknown, different unknowns here, different unknowns. The unknowns here. You can find the unknowns in each circuit. Use the properties, use the formula, use whatever you like, okay, to find these unknowns. Here, how to add the sources voltage in series, which is the same what we did. And also here, in the circuit here, you can find also the unknowns. It's a good practice to apply again Kirchhoff voltage law, the same what we did before. And voltage divider rule again, how to implement the voltage divider rule in those circuits. I recommend highly to solve these examples or tutorial. Then you get more skill to implement the formula and different ideas. When you attempt more questions, you will gain more skill of the course. Study well, gentlemen, and if you have a question, you can prepare it, then we can solve it in our class session. Thank you and good luck.